DVCon, the Unified Test Writing Framework for Pre- and Post-Silicon Verification. Abstract. Day by day, there is an increasing need of the integrating, reusing the infrastructure across all stages of product development, right from the pre-silicon design verification to post-silicon test validation, evaluation, and applications for validation. We propose a framework built on the UVM-centric digital verification environment that not only enables analog designers, test writers to write tests without having to know the complexity of the underlying UVM, but also opens up a common communication medium over which the design, test evaluation, and application can talk and exchange test and high-level functions. This framework is generic and can be used by any project, as most of the infrastructure needed to being dumped from the IP-XACT by customer generators. The old digital verification environment introduction. All the digital verification environment today are predominantly in UVM because of the verification features it offers. While digital verification community is well versed with this methodology, on the other hand, designers, both digital and analog, see that this complexity of infrastructure as a difficult task to begin with, and this makes test writing a challenge for them. Having said that, once we have silicon in lab, other language, a challenge is how we can facilitate a faster bring up of silicon on evaluation board and minimize the design and evaluation round-trip debug delays involved. Further, part 2 of this paper explained how the proposed framework solved above-mentioned challenges. Section 2, main idea. In complex SoC, a system on a chip, a project in top-level verification is likely where the design sub-blocks come together and interact. Complex configuration and use cases will be simulated in the context of the top-level system verification, and a valid concern which can arise how to address these challenges and close top-level verification with good coverage while being efficient and reusable across both pre-silicon and post-silicon. In the system-level verification, device under test DUT is likely to be controlled in a similar manner in a simulation pre-silicon as in the test evaluation applications post-silicon. Typically, there will be a relatively reduced number of well-defined interfaces between the chip and external world. These interfaces may include communication interfaces, SPI, I2C, and JTAG, and etc. General purpose I/O, GPIO, or specific purpose input, output, and protocols. Likewise, there is also a delimited number of high-level actions which can be performed on these interfaces. Read and write frame, wait on how output event, drive event, wait for a predefined amount of time. The interaction with the DUT is very similar at a system level between simulation verification and evaluation test. The main difference is that a simulation verification, it will be universal verification component, UVC component, which interact with the device, where the post-silicon will be actually the hardware which is connected to the DUT, so that the interface and actions on them remain the same. This presents an opportunity to implement a higher-level test writing framework which is common across pre-silicon and post-silicon. Only at a lower level, when the driving and monitor the interfaces, it is necessary to distinguish the specific action and the interface is handled. An implementation, such as one proposed and Figure 1, present several advantages in the deployment of the chip, such as 1. Accelerated post-silicon testing by leveraging the already developed test library during simulation verification. 2. Having a common high-level framework and test format enables seamless exchange between post-silicon and pre-silicon. This is helpful when simulating test or configurations which have resulted in a buggy or unexpected results on bench. Therefore, the proposed framework may provide a significant reduction in the evaluating times and allows for tightly coupled for between the simulation and evaluation. Well, Figure 1, pre- and post-silicon test framework. In addition to the above, if the device will also require the firmware FW to be developed, there is a potential opportunity for the functions developed in simulation verification to be used, a guideline or example for firmware developers. If the firmware development starts after top-level simulation, verification starts in this situation, there is a chance to have also leverage the function writing effort and accelerate firmware development in some extent. In order to solve first part of the problem, a bit field-centric C-based infrastructure was developed. This infrastructure consists of 1. A front-end software implemented in C and which tests are written. It provides the following features. CLA, C model of the chip register map, which is auto-generated from the IP-XACT files which consist the register information. B. Basic low-level instructions that define how to interact with the chip. 1. MMR read and write. 2. Memory read and write. 3. Analog node voltage probing. 4. Force and release digital analog nodes. 5. Waiting for a specific value on an analog digital node. 6. Delay. 7. Random number generator. C. Simplified access to the register map, allowing the read and writing bit field and registers as if they were C data types while keeping track of the state of the register map and abstracting the low-level details such as register addresses and a bit field offset. B. Ability to use higher-level range construct offered by C while letting the C compiler taking care of the parsing. E. Write a library of functions to configure the chip developed by the design and verification engineers to speed up the system-level test writing. 2. Cosim, the analog digital cosim to learn the simulation, which provides the following features. Reuse of the UVM setup and agent from the digital design verification, saving, avoiding the duplicate effort of harnessing the power of the UVM. Analog simulation to execute the analog models which are not Verilog system Verilog real number models. Make use of your functionality lent by an analog simulator from for waveform post-simulation processing. The Figure 3 C-based framework. Figure 4 is a Python-based framework. With the above proposed methodology, we were able to extend all the complex features of the digital verification, like randomization, release, force, weight on a internal digital design nodes, and etc., to the cosim infrastructure, and also has been being able to get more analog designers on board to enable more cosim test writing. The first step enabled reuse functions, test and infrastructure structures across cosim, digital and firmware verification. This solved the first part of the problem. Since the framework enabled of the reuse in pre-silicon verification effort, we wanted to extend it for the post-silicon verification as well. While C is well suited in communicating with the simulator, it is not that well suited to the communication with the lab equipment as well, though, as all the device drivers needed to talk to lab equipment have to be developed from scratch. Python being very popular language and a lot of open source community working on it seems a possible solution to bridge this gap. Two hurdles on this path were bidirectional communication between Python and the simulator SV, and all the existing test suite which was already developed in C needs a huge migration effort. As Python cannot communicate directly with SV, we had to build an intermediate bridge to solve this challenge. This intermediate bridge, as shown in Figure 5, which is transparent to the user, consists of the DPI imported exported from SV to C and a Py and C API. It is this bridge which enables us to run the already existing test suite without any change. However, we plan to fully migrate all the C tests to Python in long term to avoid or minimize infrastructure maintenance for both C and Python. This infrastructure is shown in Figure 5. This is the Figure 5, the Python and system-log simulation flow. The direct programming interface, DPI, is basically interface between the SV and the foreign programming languages. In particular, the C language. It allows to call the C functions from SV and to export to the SV functions so that they are called from C. Example code for SV and C communication through DPI shown in Figure 6. Figure 6 is SV communication through DPI. Python C application programmer's interface API provides the embedding and extending the Python. Embedding Python to insert the calls to Python interpreter into your C application and extending the Python to load the set of the C functions as part of the import statement. Example code for a PyC communication through API shown in Figures 6 and 7 and 8. And so in this example, C function command underscore main call the Python function main underscore py. In the case, the file command.py and using the embedding the Python concept as shown in Figure 7. And to call the C functions from the Python required to build the module in C module in this example as shown in the Figure 8. Anyone with the basic knowledge on Python can easily get on board with this framework to write the test cases. A sample tested case is shown in Figure 9 for reference. Figure 7 is embedding the Python. Figure 8 is extending the Python. Section 3, experimental result. The proposed infrastructure has been implemented in the product which is a 77 GHz radar sensor chip in 28 nanometer RF CMOS technology. Some of the proof of this effort are: during pre-silicon phase, C Python based infrastructure is automated test dumping for checking the connectivity from SPI to digital register bits in digital SIMs, and the same approach extended to check the right voltage levels at deep down and longer nodes in cosim. This was possible to do due to the strict net naming convention followed in the RTL and schematics. The functions and the test written. This enables function reuse across digital and cosim. And C enables the verification infrastructure of the complex data path presented in the system by using power of Python packages like NumPy to compute FFTs and etc. D enables system boot-up infrastructure with a minimal effort. E enables designers to get involved in the test development. And next is during the post-silicon phase, Pi-based infrastructure. A design shared the chip configuration library with the evaluation and applications, accelerating debug and evaluation and demo creation. B configuration from the evaluation and applications which had issued could easily be read into the design verification simulation environment to debug the issues. And C is the UltraFlex tester, has a Visual Basic front end and the chip configuration that design has developed in Python and C were translated as VB, Visual Basic code with minimum effort. So the idea was well received and well appreciated by the design and in evaluation and application teams. The figure 9 is comment.py. For conclusion, the early planning of the consensus amongst the different subsystems allowed us to specify and implement a framework which accelerated direct test development effort in pre- and post-silicon. Silicon evaluation timeline was shortened because the pre-silicon verification test and could be leveraged and used in the bench. And in addition to this, probabilistic configuration of the test bench on the bench were quickly and transparently sent back to the simulation and verification to debug the issue with increased observabilities. This allowed for the total verification time of the project to be shortened and the time to market of the project was put in, while most likely also improving silicon quality. This framework and underlying the idea helped meet the product line deadlines and increased the chances of the commercial success of the device. The DUT debug was streamlined in all stages of the top-level verification. Okay, today I read this paper, the Unified Test Writing Framework for Pre- and Post-Silicon Verification. Thank you for your time and see you next time.